This begins a brief walkthrough through this very first note packet on chemical kinetics. Remember we talked about that, believe it or not, we really do kind of depend and think about certain reactions and the time they require. For example, taking ibuprofen, you have a certain idea of when it will take effect, as long as you've taken the proper dosage, the time it takes to cook and bake food. So we've never, up until this point, actually timed reactions. Well, it's because now we're ready to actually pursue that in depth. So how long does it take a reaction to work? Can we speed it up? Can we slow it down? Can we actually control the speed of the reaction and understand it? And actually, the speed of a reaction gives insight into actually how reactants form product. These are the questions we will specifically answer this unit. This is the vital information that we need to have a grasp of before we enter into understanding chemical kinetics. This is my favorite explanation of Zumdahl as to what the chapter is about. So we're studying reaction rates, how they change over varying conditions. So really, what impacts the rate of a reaction? And what molecular events occur during it? So actually, step by step, how do we get from reactant to product? So the first question is, well, how do we actually measure the rate? What are we looking to change over a certain amount of time? Well, we can target the amount of product that we're forming or the amount of reactant that we're using. So what we're going to actually do is track the change in concentration per unit of time of a product, both products, or the decrease of the reactant. So, in essence, we're going to say that the rate of the reaction is the change in the concentration of reactant per a unit of time. Now, depending upon the reaction, the time can be seconds, it could be minutes, it could be hours, it could be days, but usually for us, it's seconds or minutes. Now remember, when something is written in brackets, we're expressing the concentration in terms of molarity, mole per liter. So we could express this reaction, the rate of it, as the change in concentration of NO2 per unit of time, the change in concentration of NO per unit of time, or the change in concentration of O2 per unit of time. Now rates are going to be positive values. So we are decreasing the rate of, this will change negatively with time because we're decreasing the quantity. So this actually will be a negative. So usually, we put a negative here to force rate to be positive. Can we look at some experimental evidence? If we look at this same reaction, what we've done is every 50 seconds monitored the amount of reactant and the amount of each product. Now, if we look at the data, can we see that we are decreasing this because, of course, that's our reactant, and increasing these? But the rate of change, or the amount of change per every 50 seconds, is not constant. In fact, here, from 0 to 50 seconds, we have a change of 0.0021 mole per liter, and then from 50 to 100, it's 0.0014, and then the next 50 seconds, it's 0.0010 molar. So we're actually decreasing the change amount per 50 seconds. Well, if we take a look at these products, do we see they're not changing equally? Well, that, of course, is per the stoichiometry of the reaction. However, the amount of this we're making equals the amount of this we're losing because of the stoichiometry. So we're going to be making as much NO as we're reacting NO2, and half of that amount of O2 because of the stoichiometric relationship. So the change of concentration with time is not the same. as the reaction proceeds, rate changes. It is not constant. In fact, graphically, and I tried to color code this a little bit for us. So it should make sense. This is time from start to finish and concentration. So we are starting with just reactant, and reactant is decreasing with time. Here are two products. Without even knowing this is NO, we should be able to tag it because we're getting a greater quantity of it, again, because of the stoichiometry of the reaction. Rate is changing. If rate were constant, it would be a linear line. The question may be, why is rate not constant during a reaction? Well, if we take a look at these boxes, and again, I tried to color code, the red being the reactant, the purple being the NO, and the green being the O2. If we just elementarily say, okay, for every two of these, we get 2 and 1. So these two made these two made these. So if we start with all reactant, we're going to say these two and these two produce product. So then, eventually these react to produce product. Now, reactants have to come into contact to produce product. As we produce more and more product, we have less and less reactant that can find itself. Also, as we're producing product, it gets in the way of reactant finding reactant. So we have less reactant to come into contact and obstacles in the way. So that is why rate changes as the reaction proceeds. Concentration has a huge impact on the rate of reaction. So as the concentration of reactant decreases, so does the rate. What I wrote on the front here, these we call rate expressions. And if we take a look at the very next page in the packet, this has this reaction and expresses these. And it should make sense that the rate of the reactant reacting will be equal to whatever the value of the production of NO, because it's a 2-to-2 mole ratio. However, these are twice the rate of the O2. So whatever these are, we're going to have to double this to be equal to these. Another way of illustrating this, let's say generically that we have 3A that yield 2B and C. Well, the rate of the reaction could be expressed in terms of A or B or C. Now, none of these will be the same numerical value because these have different mole ratios to each other. We often, though, are given the rate of one thing. So, for example, if we know the rate of A, now, rate is usually mole per liter unit of time. So let's say mole per liter second, and maybe the value is 0.52 mole per liter second. Well, if we know A, we can actually find the value of the rate of B in terms of A, or the rate of C in terms of A, if we know the stoichiometric relationship. So, I've just written these ratios, just interpreting our balance equation. So then, to find the rate of B, we would take 2/3 the rate of A. To find the rate of C, 1/3 the rate of A. And so on, if you would know the rate of B, or if you would be given the rate of C. There's a couple unit assignment questions that do this. So this would be the extent of a more complex reaction where each of these has a different coefficient. And if you would have any questions as to how I came up with these ratios, of course, you can ask me in class. All right, so these are rate expressions. But most often, we actually reveal the impact of reactant on rate through what we call rate laws. Rate laws. So we're only going to consider in this chapter forward reactions, nothing in equilibrium. So then we're just going to look at really the impact of reactant concentration on the speed of a reaction. So as I've written here, here would be a rate law generic, where it's calling reactant A and this exponent N. This would be where we had one reactant. This would be a rate law if we had two reactants. All right, so let me just kind of break down. A rate law, this is often called the differential rate law. So rate expression, but then differential rate law. And we often drop that adjective and just call it rate law. Its rate equals K times the reactant, why don't we just generically call it A, to some exponent, and I'll just call that N. All right, so this is the rate. It'll be mole per liter and whatever the unit of time is. K is called the rate constant. It is a lowercase k. The rate constant is dependent upon the experiment, but also temperature. So if you change the experiment, K value will change. If you change the temperature, the K value will change. All right. The concentration of A in mole per liter, and N is called the order of the reactant. It shows and reveals the role of A, or the reactant, on rate. Orders can be fractional, but usually they're whole numbers. In fact, the majority of orders that we will see are first, second, and zero order. Okay, what do we mean by that? All right, so let's say that the reaction is first order in A. Well, then that means whatever change we make to A, it has the same impact on the rate. So if we double A, the rate also doubles. If we triple A, the rate also triples. So whatever change we make to the concentration, it has that same impact on rate because the power on the concentration is 1. If the order is 2, so the terminology we'd say is it's first order in A, or A is first order. We'd say here that it's second order in A, or A is second order. Well, that means whatever we do to A, it will have a squared factor on rate. So if we double the concentration of A, so double the concentration of A, it will quadruple the rate. Because of course, if we double A, then our rate 2 squared will be increased 4-fold. If we triple A, well then the rate will be increased 9-fold. If it is 0 order, whatever change we make to A has no impact on the rate. So if we double A, nothing's going to happen to rate because of course something to the 0th power is just 1. So whatever we do to this, cut it in half, nothing's going to happen to the rate. We can have also fractional, and so usually what we'll see is maybe half orders. And so that would, whatever we do to A, take the square root of it, and that's the impact on the rate. but most often we have first, second, and then zero order reactants. You can, of course, have reactions that have multiple reactants, and they each can have different orders. We could have a reaction that is first order in A, but second order in B. So that is the basic presentation of a rate law, lowercase k, called the rate constant. We have the potential for each reactant concentration to play a role on rate, but the exponent shows us really the impact that each reactant has on the rate. Stay tuned for more information, particularly about how we use experimental information to come up with the rate law.